All right, welcome to week 6. This week we're going to have a look at geospatial data. Geospatial data keeps track of things that occur at some location on Earth, where the location may be an important piece of information about what's going on. Geospatial events can be fixed in place, such as, for example, a road or a mountain or something, or they can be dynamic. That is, you might be able to keep track of moving vehicles or moving satellites or something like that. We're not going to look at anything that dynamic. It combines together location information, the usual attributes and characteristics or features of some data, and sometimes there may be a time series element to this as well. Here is a famous early example of some geospatial data. This is a graphical description of a cholera outbreak in London in the 19th century. The source of the disease was not known, but Dr. John Snow believed that it was probably caused by contaminated water. And so what he did was he put together this map of London, at least the area where the outbreak was occurring, and these red circles here indicate the number of deaths due to cholera at various locations around the city. And what he was able to discover in this way was that there was a certain water pump at this location, sort of right smack in the middle of the graph, around which most of the deaths seem to be centered. And the local government was persuaded to try to mitigate the cholera outbreak by the simple expedient of taking the handle off of the pump so that people couldn't use it. So this did two things. First of all, it added some evidence for the idea that cholera was being spread by contaminated water. Also, later on, it was found that the well where this water was coming from was in fact, or had in fact, been contaminated by sewage. So with this graphical evidence, it's abundantly clear to, any reasonably intelligent person that there appears to be a concentrated problem around that particular water pump. Without this information, it would all have just been, argument and conjecture. There are various tools available for doing geospatial analysis. One commercial product is this thing called ArcGIS, and some open source things include QGIS, and Carto is a commercial product, but apparently available for a much reduced cost nowadays. And then there's Google Earth. So all of these things are used for doing geospatial analysis with various levels of sophistication and flexibility. We are going to take a look at a tool available for Python called GeoPandas. And basically what this does is to add support for geographic information to the usual pandas objects. So a geoseries is simply a kind of series that has geographical elements layered on top. And likewise, a geodata frame is a kind of data frame that has geographical elements on top. Now, GeoPandas does not come as part of Anaconda. If you have installed Anaconda as your package containing Python and NumPy and pandas and so forth, then cross your fingers, start an Anaconda command prompt window, not an ordinary command.com Windows command window. And in your Anaconda command prompt window, type conda install geopandas. And with any luck, it will work. You may, in addition, discover that you have to separately install GeoPy and Archery. Or you may discover that you have other kinds of problems. Now, I was able to get conda install geopandas to work fine on my system. There were some things that I wanted to demonstrate that I was not able to get working. Consequently, I am not planning to put together a homework assignment that includes this material, because I am not 100% sure that everybody in the class will be able to get things working. So I hope you are able to get GeoPandas installed and working, and that you'll be able to follow along with the examples that I'm going to go through in this lecture. Okay, well, once you have installed GeoPandas, you want to launch whatever your integrated development environment is. These are primitive idle prompts. You should, of course, be using Jupyter Notebook, preferably. Let's give these things a try, and we'll see if I can get these all to behave. I'm going to be using idle as, since I'm lazy. All right, so here is idle, and I'm going to first try to import GeoPandas. The conventional abbreviation for this is GPD. And it worked. Shapely is a module that GeoPandas makes use of for providing various graphical forms. And Archery is also something used by GeoPandas in the plotting code. So those imported fine. And now I'm going to import the usual suspects that I tend to need anytime I'm analyzing data or doing graphics. So NumPy as NP, pandas as PD, matplotlib.py, plot as PLT, Seaborn as SNS, and I want to not have columns dropped from my pandas data frame display. So I'm going to do my usual set option of display.max columns to none. All right, well, so far so good. Now, let us find some data. All right. Now, data for geospatial analysis that you can use in Python comes in a variety of different formats. There are ancient DBase database files that contain map information. DBase was a consulting job that I had in the very late 1980s. DBase was kind of the big database system that people used on IBM PCs and compatible machines under MS-DOS way back in the day. Then there's something called keyhole markup language and zipped keyhole markup language. This is the kind of formats used by Google, Google Earth and Google Maps. There's another format, .shp, for shapes. And we're going to make use of GeoJSON files in here. Now, this is a formal specification, and I know this is a little bit tiny on this slide here, but there is an honest-to-goodness RFC number that describes this specification for GeoJSON. And basically, in GeoJSON format, this is JSON format. It looks somewhat like a Pandas dictionary, but it is not. We have three named objects: type, geometry, and properties. And within these, there can be subproperties. I'm not going to go into that in much depth, but if we find a file whose name ends in .geojson, we can assume, until proven otherwise, that it adheres to this standard. Well, let's see if we can find some GeoJSON data available about Pittsburgh. So let me pull up Google, and Pittsburgh. You can see I've done this before. GeoJSON. I don't need the caps. GeoJSON data. And sure enough, many governmental organizations do provide data available to the public, often in GeoJSON format or various other formats. So let's click on this Allegheny County, City of Pittsburgh, under data.gov. Actually, that may have been slightly off the screen for you. Anyway, so Allegheny County, City of Pittsburgh, Western PA is what I clicked on. And up comes this web page that tells me that there are 129 data sets available within the Allegheny County / City of Pittsburgh / Western PA Regional Data Center area. And since we're doing geographic stuff, let's start by just taking a look at the boundary of the city of Pittsburgh. Let me go ahead and click on GeoJSON. That will download an appropriate file for me. And you can't see that, but it did download the file for me. And I will go to where that file is. All right, so here's my lecture support files directory, and here's my Pittsburgh City Boundary.json GeoJSON file. Let me type in the code that will allow us to read and interact with that. Okay, I'm going to use GeoPanda's read file function. I have that saved in a different file, so I can just copy and paste that into my shell. And this is going to be a GeoPanda's a geodata frame object, and I have read this Pittsburgh City Boundary GeoJSON file into that data frame, geodata frame. So if I ask for the type of this thing, sure enough, it's a geodata frame. And if since it's a data frame, it has a shape, and it is 8 records with 9 columns in each record. Let me just display the first couple of rows. PGH boundary. Pittsburgh boundary is what PGHB stands for. And I'm going to just see the first couple of lines. Okay. And what we have here is a field identifier. We have the area of the region, the length of the perimeter of the region. Not sure what boundary and boundary I are about. But eventually we have this geometry column, which is all these multi-polygon records. And the GeoPandas plot function knows how to process these things. So let's try doing pgh boundary dot plot and plt dot show. All right, there we go. So there is the boundaries and therefore the the interior of the city of Pittsburgh. Now there are 8 rows because there are 8 different components in here. Let me grow this guy so that we can see more easily. That was I clicked the X by accident. Let me plot it again and show it again. All right, let me stay away from that X in the upper corner. Come on now. So, supposedly there's 8 regions to this plot, and if we stare, we can see them. There are some that are a little tiny, so we've got 1 and then a bigger one. 1, 2, 3, 4. Then we've got a huge one here, 5, and another fairly huge one, 6, 7. Now, right in here, you may be able to see a pale white outline around a filled-in component. That is actually Mount Lebanon. And Mount Lebanon is enclosed within the boundary of the borders of Pittsburgh, but it is not part of the city of Pittsburgh. It is a separate. It has its own separate government. So that is the 8th component within the boundaries of Pittsburgh. Okay, so there's our very first geoplot. And there we are. Let's see if we can get a little more detail. Instead of the city as a whole, let's find out about the neighborhoods within the city of Pittsburgh. I'll return to, well, I won't bother. I was going to say I'll return to Google, but here's the result that I get. If I search for the neighborhoods of Pittsburgh in GeoJSON format, what I will discover is this GitHub repository that has an enormous amount of information about cities literally all over the world. And if I go to, if I click on that particular link, I end up with this visualization. And you can see here that we've got, Africa, Akron, Ohio, Alameda, California, Albany, New York, on and on and on. And this little icon here in the upper right is the download icon. I did click that, and that downloads this file called Pittsburgh GeoJSON. So let's give this a try. Let me into PGBN for PGHN for Pittsburgh neighborhoods. Let me do my GPD, read file, Pittsburgh.geojson. And I do get a couple of warnings. These are future warnings about things happening inside of one of the libraries that's being used that are deprecated and that may become unavailable in the future. So for now, it's not a problem. We can get away with using these things. And presumably by the time this deprecated stuff is taken out, the GeoPandas library itself will have been updated. All right. Well, once again, this is a geodata frame, so it does have a shape, bghn.shape. Okay, so this is telling me that there are 90 rows. I'm going to make an assumption that that means there's 90 neighborhoods, and that each neighborhood is described by 5 columns. Let's just take a look at the top of this. pghn dot head. Just take a look at a couple of rows. Here we go. Yep. Okay, so here is the name of a neighborhood, Southside Flats, with date and time information, when this was created, when it was most recently updated, cartographic database ID, I suppose. I'm not sure what that field means. And then here we have the geometry, which is another one of these multi-polygon objects. Let's give this a plot, see what we get. PGH neighborhoods plot, plt.show, and cool. So you can see that this is much more detailed. Maybe difficult to see in the video, but if you try this yourself, you'll see all of these regions that have these thin white outlines around them. And we are in central Oakland, which is right about here. Okay. Alrighty. Let's take a look at, first, all of the column names. Then we're going to take a look just at the name column. All right, so PGH neighborhoods, Pittsburgh neighborhoods dot columns, name, created at, updated at, etc. Let's take a look at Pittsburgh neighborhood dot name column. Okay, and indeed there are 90 neighborhoods numbered 0 through 89. And some of these, frankly, I'm not familiar with. I don't know where Southside Flats and Southside Slopes are. Hazelwood, Mount Washington, Squirrel Hill South, West End, Glen Hazel, these are all things that I recognize as being neighborhoods. Let's see if we can locate the neighborhoods right around Carnegie Mellon, including where an awful lot of the students live. All right, so partly as a reminder here, I'm going to do this using a regular expression library module. So we're going to import RE, and then for each name in that name column, we're going to search in that column for to test whether the name of the current row matches Oakland or Shady or Squirrel Hill. Okay, so remember that the way the re.search function works, the first argument is a regular expression pattern to search for, and the second argument is the string to compare to the regular expression. So if nm is my for loop variable, which contains each name of a neighborhood, one name at a time. If that name contains OAKL or shady or squirrel, then we have a match, and we're going to simply print out the name that matches. And we should get this list here. Squirrel Hill, I guess most Pittsburghers think of it as just one neighborhood, but perhaps real estate agents think of it as two. We've got Squirrel Hill north of Forbes Ave, and we've got Squirrel Hill south of Forbes Ave. And then Shady Side is north of Fifth Ave, north of Squirrel Hill North. And then right around us, Oakland is divided into four pieces. All right, well, let's confirm that this search does in fact find the neighborhoods that we know are right in our vicinity. Let me pull up my here we go. And let's go ahead and type in this code. Okay. So we're going to import RE so that we can use RE.search. And then we're going to say for each name in pgh.name column, if a regular expression search for the pattern OAKL or, okay, vertical bar for or, shady, or, SQUIR, whoops, it's got to be a capital S. If Oakle or shady or squirrel matches NM, or if NM matches that pattern, really, I simply want to print that name. And yes, I do get the regions that I expect: Oakland, Squirrel Hill, Shady Side. And turns out that they are split up into various components. Now, I want to get this collection of names into a list. And I can use basically the same for loop. I'm going to embed that for loop in a list comprehension. Let me copy and paste that list comprehension from my code file. Alrighty, so here we go. I'm doing a list comprehension. Here are my square brackets around this entire thing. What's going to be put into the list are names. I have a for loop to loop through all the possible names, but the only ones that are going to end up in my list are the ones that pass this if test. Okay, so for each name in the Pittsburgh neighborhood names, if the name matches one of these possible patterns, Oakle or shady or squirrel, so that we get back a match, which is not equal to none. All right, so if that if test is true, then that name will go into my list, and we can see that yes, near is a list of the 5 neighborhoods that I want. Now, I want to create a sub data frame, a sub geo data frame of the Pittsburgh neighborhood data frame. I want to get a sub data frame of that only includes the nearby neighborhoods to Carnegie Mellon. The first thing I'm going to do is to generate a Boolean index. in the following way. Now that I have my near list, well, the formatting here didn't look so wonderful. Now that I have my near list, I'm going to say, let's take the Pittsburgh neighborhood name column, and to each value, let's apply this lambda. For the current name, return whether name is in this near list. So I've got 90 rows. Therefore, I will get 7 true values and 83 false values. I'm not sure we'll see any true values in the result that's displayed here. We did. We got 1 that's true, but most of what we're seeing here is false. But that's fine, because we can then use this Boolean index to select a subset of the Pittsburgh neighborhood data frame. We're going to call this Pittsburgh neighborhood near, and it's going to be Pittsburgh neighborhood sub, and then this Boolean index. All right, Boolean index, close square bracket, and here's my PGH neighborhood near neighbor, and it's only got 7 rows in it. All right, we've got Squirrel Hill South, Squirrel Hill North, Shady Side, Central, Northwest, and South Oakland. I can just display the name column of this, so PGH neighborhood near dot name is just those 7 names. I can display the geometry column. I misspelled it. PGHN near. So Pittsburgh neighborhood near dot geometry. All right, and the geometry is all these multi-polygons. Within a geometry object, it turns out that a boundary is defined. And this, again, this is part of the standard for this GeoJSON format. Geometry is a standard component, and within the geometry, boundary is also defined, and these are multi-line strings. These, of course, are latitude and longitude values. And this boundary is something I can plot. So let's give that a try. I'm going to take the boundary and plot it. And when I do plt.show, how extremely cool. I am able to see the boundaries of these 7 neighborhoods. So these 2 things to the right and the lower right, the lower one is Squirrel Hill South. This blue line is Forbes Ave. The upper part here is Squirrel Hill North, and the blue line at its upper edge is 5th Avenue. And then here we have Shady Side, and its upper boundary is Center Avenue. Okay, there's a little pocket of Shady Side Hospital that's considered to be in Shady Side, even though it's on the other side of Center Ave. And then over here on the left side, we have the 4 components of Oakland. We've got Central Oakland, and then Northwest and South Oakland. Now, if you look at the map, you'll see that technically speaking, Carnegie Mellon is in Squirrel Hill North, although as a Pittsburgher, I almost always think of it as being in Oakland. It's it's just right on the border of Oakland. So that's pretty slick. Next up, okay, so there we have our outline of the 7 nearby neighborhoods near Carnegie Mellon. Next up, I want to take a look at a bit of plotting configuration stuff. It's possible to create subplots and to put those into a figure of a certain size. So I'm going to say plt.subplots. I want 1 row and 2 columns. And this is going to allow me to create 2 plots, one in each of these regions of the subplots. Now the overall figure size is going to be 10 wide and 5 tall. That gets scaled, so the specific numbers here don't actually matter all that much. I just want to be sure that I have a 2-to-1 ratio, that the overall figure is twice as wide as it is tall. Now, what this subplots method does is to return a tuple of 2 components. The first component is a figure, and this little description here tells me that it's 1,000 pixels wide by 500 pixels tall, and that it contains 2 axes. The second thing in the tuple is an ND array of the axes, since there are 2. Okay, so I've got an ND array of the 2 different axes for each of the 2 different figures. This actually does create a figure, but it's a figure that doesn't contain any plots. So I'm just going to say plt.show to show that empty plot, so that we can then go on and do more interesting things with our plots. So let me type that stuff in. Whoop. All right, so I'm gonna say plt.subplots, 1 row, 2 columns. The overall figure size is going to be 10 by 5, and that gets scaled up automatically. Oh, I do this every single time. I don't know why. Fig size is not a function. Fig size is a parameter name, so I need to say fig size equals, and then this tuple 10 by 5. There we go. What did I forget? What did I forget? Oh, subplots. I misspelled subplots. Subplots. Sorry about that. There we go. And so here we have the figure with its sort of rudimentary description, and I have this ND array of axes. And when I do plt.show, you'll tell that I have, yes, just empty plots, empty side-by-side plots. All right, now let's actually create a more meaningful plots. Because subplots returns a tuple, I'm going to use the sequence unpacking idea to do a multiple assignment here. The the figure is going to be referred to by this variable called fig. And the ND array of two axes is going to be referred to by this variable axes. All right, so fig, if I look at fig, I see that it's that figure. If I look at axes, I see it's that ND array with two axes in it. Now, for the figure, for the overall figure, I can set an overall title. This is the super title of the entire figure. Okay, and it's a text item that's going to appear. And now I'm going to plot my Pittsburgh neighborhoods in the left side of the figure. Okay, so the axis for the plot of the Pittsburgh neighborhoods is going to be the left side of the figure, axis sub 0. All right, nothing shows up until I eventually do a plt.show. I also want to define a title for that part of the figure, for that axis. So axis 0, I'm going to set a title of filled. You may recall that our plot of the Pittsburgh neighborhoods had all of the neighborhoods filled in with blue with this pale white outline around each one by default. All right. I also want to do the boundary plot that I did. That's going to go in the right side of the figure. And here, instead of accepting the default blue coloring for the boundaries, I'm going to set the color to K, which means black. Okay, so you can look up all this color stuff. If you look up matplotlib colors, you'll see that there are 8 one-character predefined colors. Red is R. Green is G. Blue is B. So far, so good. Then we have white, which is W. Black is K. Why is it K? Well, the blue took precedence, so B is blue, K is black. Obviously, right? And then we also have cyan, magenta, yellow as an alternative to red, green, blue. So we've got cyan is C, magenta is M, and yellow is Y. Those are the simplest one-character colors that you can request. But it turns out you can also request other kinds of colors found in the Seaborn color library. You can specify colors by bit patterns, red, green, blue values. There are many, many, many ways of specifying colors, and if you're interested, you should just look up matplotlib plot colors, and you'll find days worth of documentation to read. All right. I'm also going to create a title for the boundary plot. And the boundary is going to be the outlines of the neighborhoods in black, whereas the filled neighborhoods themselves are all going to be in blue. All right, well, I have now created a figure that contains two axes. I've specified a super title for my entire figure. Then I have put the Pittsburgh neighborhood plot, the filled in blue, the default blue colored filled in neighborhoods on the left side, axis 0, with filled as its title. And then the boundary plot, which is with line boundaries that are black, on the right side, axis 1, and set its title. And finally, we're going to be able to say plt.show, and poof, up it comes. Okay, so the purpose here was basically to show you that you can request different plots in different parts of an overall figure of a certain dimension. My dimension here was 1 row and 2 columns of plots within this overall figure. Here's my overall figure title. And then I've got my left side plot and my right side plot. That is my axis sub 0 plot and my axis sub 1 plot with the individual titles for these images. Okay, so that's that. There we go. Now, we can also combine both of these plots together into a single figure. So this time I'm going to create a single figure, 1 row, 1 column, and I'm going to put both plots into the same axis. Now, since this is 1 by 1, and therefore there's only a single axis value rather than 2, I do not get an ND array of axes, I just get a single axis. Let's confirm that that actually works as I claim. I'll copy that from my code file and paste that into my shell. Whoops, that was supposed to be fig, not ig. Let's try that again. Actually, I better say plt.show so that one gets cleaned up. All right, so there's my empty ig. Now let's try this again and say fig instead of ig. Okay, so fig is square, 500 by 500. An axis, instead of being an ND array of 2, is just 1. All right? So now I can set my overall figure super title, as I did before, to the same thing. But this time I'm going to put both of my plots, the filled plot and the outline plot, the boundary plot, into the same axis. I'm using the cyan color here rather than the darker blue, just for a change of pace. That's my neighborhood plots. And then I'm going to have my boundary plot on the same axis, okay? And it's going to be a black border. And here we go, plt.show. And there we go. So I have both the filled in areas and the black boundaries shown in the same axis, in the same figure. And notice this little white region in here, that, as I said before, that's Mount Lebanon, which is not part of the city of Pittsburgh, even though it's surrounded by things that are. Most of these neighborhoods, by the way, historically, these were separate towns. Pittsburgh was once a town at the right at the confluence of the Allegheny River and the Monongahela River to form the Ohio River. And over time, Pittsburgh absorbed all of these surrounding towns, agreed to be included into Pittsburgh, and that's why in Pittsburgh we have these very distinct neighborhoods with kind of definite boundaries, because they did all used to be independent towns. Okay. Well, let's take a look at another somewhat more interesting data set with a little more depth to it. SNAP is an acronym for the Supplemental Nutrition Assistance Program, which in earlier, less politically correct times was called the Food Stamp Program. SNAP is important to two different groups. One group, obviously, is the recipients of the aid. The other group is farmers who sell food, and farmers are very delighted when the government, makes money available to people to buy food with. All right, so this SNAP program each year tends to be part of what's known as the Farm Bill. Okay, so if we search for SNAP within this data.gov area for Pittsburgh, we do find that there is one SNAP data set. And let me pull that up, because before we look at the actual data, I want to look at the description of the data. So we're going to click on HTML first. All right, let's search for SNAP. There it is. And now we'll look at the HTML. Okay, I need to shrink this window down so that it is all visible within my recording boundaries. Whoopsie. Come back here. All right. There we go. Okay, so we've got a map of the various neighborhoods of Pittsburgh, and we're told that this is information about the SNAP data. View full details. Alrighty. Data related to the PGH SNAP project. Please note that this data is not up to date. It was created with 2010 census data and early 2010s data for non-census related data. Historic data is considered to be accurate at the time it was captured. So, although it's called the SNAP data, this data set has a huge amount of information unrelated to the Supplemental Nutrition Aid program. And each of these has a fairly obscure. These are the columns that exist within the geodata frame that we'll look at. Area, perimeter, hood. That's actually an abbreviation for neighborhood. That data is actually duplicated because we also have neighborhoods. So hood and neighborhood actually contain the same information. Then we have the populations of each of the neighborhoods at various census changes or at various census years. Land area in square miles and an acre. Population density. Percentage of various ethnic groups. Percentage of various age groups. Who, what living units are available, which ones are occupied, which percentage is occupied by owner, which by renter, how many were built at various times, how many foreclosures there were. All right, I mean, we've got an enormous amount of choices here, and I'm going to start out by looking at the foreclosures that occurred in 2010. Remember that, well, you may not remember, but 2007, 2008, that was the period of the United States real estate market collapse, which caused shockwaves of serious financial problems throughout the world. And let's take a look at how many foreclosures there were in the various neighborhoods during the year 2010. Okay, so we will download the data. I'm going to go back to, okay, I guess, I'm sorry. So, all right, so I opened this snap data. I just need to close that window to get back to the data center interface. And then I can download the GeoJSON data directly. It's in a file named Neighborhoods with Snap Data GeoJSON. So let's go ahead and read that data file in. All right, so I will do this in my shell. Here we go. I'm calling this Pittsburgh Snap. That's going to be the name of my geodata frame. And I can find out its size. Whoops. I didn't mean to try to display the entire thing. Let's try that again. PAGH snap dot shape. Okay, 90 rows. There are, as we already know, 90 different neighborhoods. Look at this, though, that we've got 193 different columns available. Let us have a look at the columns. All right, and these are the first 10 and the last 10 or 11 of the of what we're looking at. Now the geometry here is going to be the same, we presume, as the geometry for the other Pittsburgh data sets that we looked at. Let's just confirm that to be sure. So I'm going to create a figure with just one axis, and into that we will plot the boundary, okay, PGH snap, geometry, boundary, plot. This is going to have black edges with a line width of 1 and okay, that's just the line boundaries. Now actually what I want to do is I want to show the foreclosures for each of these neighborhoods, and I'm going to do that using a color gradient. Okay, so the lowest number of foreclosures will have light colors, and the highest number of foreclosures will have dark colors. So this is going to require me again to do 2 plots in the same figure. Let me recreate my figure once again, and we will arrange for the black boundaries. But this time, we're going to just plot the foreclosure column, and this is going to require some discussion. All right, so our column is snap all, not sure what CSV stands for, frankly, foreclosures in 2010. Mako is a color gradient scheme from Seaborn. Sorry. Okay, so Mako is a color gradient scheme from Seaborn. You can look up all the Seaborn color schemes, and Mako is one of them. This tag here, _R, means that I want to reverse this color scheme. In the default color scheme, the high values would be dark and the low values would be light, but I want the reverse. I want the high values to be light. No, I take that back. I take that back completely. I want the low values, the low number of foreclosures to be light, and the high number of foreclosures to be dark. So I need the reverse of the Mako. I am going to be treating, despite the number of foreclosures is numeric, I'm going to be treating it as categorical. I do want to see a legend on the screen, which is going to show the color for each of the possible number of foreclosures. All right, so for each of the number of foreclosures. Now, some keywords, some added keywords for the legend itself. I want the legend to be located at the right of the figure, and I want the formatting of the values not to have any numbers after the decimal point. All right, let's see what we get. plt.show. And here we go. Let me grow that so it's a little easier to see. Uh-oh. Come back. There we go. All right. So in our immediate neighborhood, it looks like there was a very low number of foreclosures in central Oakland, a fairly high number of foreclosures in south Oakland. A bit high number of foreclosures in Squirrel Hill North. Now, Squirrel Hill North is where a lot of the fancier houses are in Squirrel Hill. It is a known thing, surprising thing, but a known thing that although poor people do have a tendency to have more trouble with not being able to pay their mortgages and therefore falling into foreclosure, It turns out that high-flying, risk-taking professionals also have a higher than average foreclosure rate. So we've probably got a lot of reasonably well-off young professionals in this North School Hill area, but they have a higher rate of foreclosure than either Shadyside or Squirrel Hill South. Anyway, and then we've got some areas that have, I think these are, I'm not sure exactly what these neighborhoods are, but neighborhoods with a lot of economic problems. So that's pretty neat to be able to see visually where foreclosures are uncommon and where they are common. This little area here, which has a very low foreclosure rate, this is right around Allegheny General Hospital. And of course, Central Oakland is where the University of Pittsburgh and the University of Pittsburgh Medical Center are located. All right, so that's that one. Okay. Let's take another look at the population density of the various neighborhoods around Pittsburgh. This one, frankly, surprised me. I thought it was very interesting. So, again, we will create a single figure. And create our black borders around the neighborhoods. We will also put in the population density for each of the neighborhoods. And this time I'm not going to try to create a legend. Oh, the legend. I'm not sure I even mentioned the legend. But the legend is this thing that, as I requested, is on the right side, and that shows what each of the colors means in terms of the number of foreclosures that occurred. Okay. All right. So we're going to use the persons per square mile in 2010, and then let's have a look at this. PLT.show. And I've chosen yet another of the, I think that this is a Seaborn color scheme, spectral. Literally follows the spectrum from darkish blue up through green, yellow, orange, and red. So the highest densities will be the dark blues, and the lowest densities will be the reds. And here we go. It's a kind of a pretty lurid color scheme. But I was momentarily surprised and then realized that I was dumb for being surprised. That Central Oakland and North Oakland are two of the most densely populated areas in Pittsburgh. I thought, well, they're just full of schools and museums and stuff, but of course they're also full of students. Okay, and so we've got an enormous number of students living in Central Oakland, North Oakland, Shadyside, other areas right around the colleges, and then in these red areas where we have quite low population densities, like this red strip right here. Well, it's funny I called it the strip. This is actually the strip district which is where an enormous number of shops are located, but very little in the way of people living in that area, or at least not in 2010. There have been some very fancy apartment buildings that have opened along the river there in very recent years. All right, well, so that is a introduction to making use of geodata frame and geoseries data. That's just one of the kinds of data formats that geographical data can be located in, with a little bit of demonstration of different color schemes and how to create either single figures with multiple plots or multiple figures, multiple plots separated in the same figure. So there we are. That's it. Have a good day.